Hello, this is Mr. White, and this video is on natural logarithms integration, part 1. And the first thing you'll notice in the 4 exercises for today is that natural log is not necessarily present in the problem from the outset. Other than this occurrence right here, we don't see natural log in the integrand. We have to train ourselves to anticipate when natural log will be part of our antiderivative though. So let's get to it. Now, even if you were to look at this and be a little bit stumped right off the bat, your instincts might tell you, I wonder if it'll be helpful to distribute that numerator. And often it is helpful to distribute numerators. So let's go ahead and do so. X squared minus 4x over x cubed minus 6x squared minus 7 dx. And again, this is where we just have to train ourselves to identify the pattern that's going to give us the natural log function. And of course, the pattern I'm referring to is the u prime over u pattern. We know that the derivative of ln u is going to give us u prime over u. And therefore, its integral, the integral of u prime over u dx, is going to give us the ln of u in return plus c. Now, I'm trusting that in class we've discussed why we need the absolute value bars there, or if we haven't, we certainly will need to do so. So the main giveaway, at least when you're dealing with a polynomial over another polynomial, the main giveaway that you might be dealing with a natural log function is when you notice that the degree up top is 1 less than the degree down below. And when I say degree, I'm referring to the exponent. That when you see an x squared up top and an x cubed down below, that's a clue that we may be dealing with the u prime over u pattern. So we look at the denominator and say, okay, if that is to be a u function, what would its u prime be? And in this case, we see that u prime would be 3x squared minus 12x, and then minus 0. Now, it's not exactly equal to the numerator, but it sure is close. I don't really need the minus 0 there. And we see that this u prime is exactly 3 times the numerator that we have here. So, since all we have to do is multiply this numerator by a constant in order to make it equal to the derivative of the denominator, then let's go ahead and do that. Let's go ahead and multiply that numerator times 3, and then to balance that out, we'll put the 1/3 on the outside. So again, we've just created a situation where the numerator now does equal the derivative of the denominator. So now when we integrate, we know we'll get ln of absolute value of that denominator, x cubed minus 6x squared minus 7. This 1/3 will come along for the ride. And of course, we need a plus c. And that would be our final answer. So let's check by differentiating. There I've differentiated our answer, and I see that, sure enough, the denominator is the denominator of our original integrand. I see that 3x squared up top divided by 3 gives me x squared, just like x times x gives me x squared. And I see that this minus 12x up top divided by 3 would give me minus 4x, just like down below, minus 4 times x. So, check. All right, let's go on to the next one. Looking at this second exercise, we may be tempted to try to draw some comparisons to the first exercise. We may see that, yes, this polynomial is the same as this polynomial, and this x minus 4 does appear in that exercise as well. However, the fact that this x cubed, this cubic function, appears in the numerator up here, but the denominator down here, and same with the x minus 4, they're in opposite positions in the fraction, that's a big deal. The absence of this x right here, that's also a big deal. So don't expect to really see any similarities between these two antiderivatives. Natural log is involved in both cases, but that's about where the similarities end. So let's get to this second one. Right off the bat, it definitely does not fit the u prime over u pattern that we saw in the last exercise. Now, if there were an x to the 4th down here and then an x cubed up top, then that might indicate that we're onto something. But in this case, when you have the degree up top, when you have a third degree polynomial up top and just a first degree polynomial down below, when the degree up top is greater than down below, that typically means we're going to need to do some polynomial long division. Now, off the top of my head, I can think of about 4 different ways we can go about doing this long division, and I invite you to just choose whatever method is most comfortable for you. I personally don't tend to use this kind of old-fashioned structure here when I'm just doing calculus myself, but I'm going to do it here in the video because most students seem to cling to this method. Now, one thing we may remember about this method is that when we're missing a certain degree, so for example, we have x cubed, x squared, but we don't have an x. We go straight to the constant next. So we insert a placeholder. So plus 0x here. And remember how we do this is we initially ignore everything but what you see displayed here, and we say how many times does x go into x cubed? And the answer is x squared, so we'll put that up here. Now I reveal these and say, okay, let's do x squared times x minus 4, and that's going to give me x cubed minus 4x squared. I'll do this minus this, and if you find it helpful, reverse the signs, do negative and plus, and then just add them instead. And we see that we're going to get negative 2x squared here. We'll bring down that 0x, just like with regular long division with numbers. And then we say, how many times does x go into negative 2x squared? Well, we'll say it goes in there negative 2x times. So negative 2x times x minus 4, that's going to give us negative 2x squared plus 8x. Again, reverse the signs if you like. Make that a plus and make that a minus, and we will get minus 8x, negative 8x. Bring down the minus 7 from above here. Ask ourselves, how many times does x go into negative 8x? And we put a negative 8 up here. We multiply negative 8 times x minus 4, and that's going to give us negative 8x plus 32. One last time, reverse the signs, minus, and that gives us negative 39. Now, back in grade school long division, you have the option of putting remainder negative 39 in this case, but that's not what we're going to do. Recall that you also had the option of adding a fraction of this numerator divided by this as a denominator. That's what we're going to choose to do. So we're going to add negative 39, I'll just say minus 39, over x minus 4. Now, what did that do for us? Well, this long division is telling us that this result is exactly equivalent to this original integrand. So what that means is that we can antiderive this instead of the original integrand. They're really the same thing. And when you look at that, that's something that we know how to antiderive, right? So let's take this, let's copy this down on the page, and let's antiderive that instead. Antiderivative dx. All right, antiderivative of x squared is going to be x cubed with a 1/3 in front. Minus 2x, that's going to give us minus x squared. Minus 8, that's going to give us minus 8x. Now notice that this last term kind of fits our u prime over u mold. If we think of this on the bottom, this denominator being u, then u prime would just be a 1. So we really want to see a 1 sitting up here, right? So let's do it this way. Let's rewrite this last fraction, or really just, if you can just picture it in your head, as being negative 39 times 1 over x minus 4. We now have our u prime over u pattern here. And when we integrate, that negative 39 will just be a constant multiple out in front, and we'll get minus 39 ln of that u value, or more specifically, ln of absolute value of that u value. And then finally, plus c, because we're anti-deriving. And guess what? That is our final answer. Now, this is another one of those rare cases in which I'm going to say, in all practicality, I don't really expect that you will derive this to verify that you get back to the original integrand. So again, we'll leave it to class time or office hours to discuss how else could we go about trying to check our answers. But for now, let's go ahead and go to the next exercise. This one is a really tricky one. And as far as coming up with some sort of general guidelines on how you can find the path for yourself, I have to be honest, I'm coming up a little bit short. So this is the type of problem that I've seen in numerous textbooks. I've seen in numerous AP prep books and AP practice exams. And once you can see the solution, you're just going to need to kind of tuck it in the back of your brain and keep it for future reference. So of course, I challenge you to pause the video and see if you can figure it out on your own. But let's proceed. If we really are just looking at this and we're baffled, we may think, I wonder if I can unchain this. Well, you'd probably try that and would come up short. You may try U-substitution, and then you'd have to figure out what U value to pick, and honestly, it's not easy to decide. So what do we do? Well, we may think, okay, I at least know that algebraically, using my log properties, I can take that 3 and I can bring it in front of the natural log. That's our log power property. And once I've got that out in front, we know we can bring that constant outside of the integral. But then we're back to this point of feeling like none of the current techniques that we know are really helping us out. So here's what a clever person might do next. They might say, okay, I know that x down on the bottom, I can't ignore it, but I'm just going to temporarily cover it up. And I'll ask myself, if I'm looking for a u prime over u pattern, if this were my u, what would the u prime be? And we'd go, oh, u prime would be 1 over x. And then we say, well, I don't see a 1 over x in the numerator, but aha, there is that x down in the denominator. And as much as we generally try to avoid the fraction within a fraction situation, in this case, it's going to help us out. So let's divide that x up into the numerator. In other words, let's do divided by x in both the denominator and numerator. And that essentially gets rid of this x down in the denominator. And we can rewrite the numerator as 1 over x. And with just a little clever algebraic manipulation, we've now got a u prime over u pattern. So it's worth pointing out that typically when we have the u prime over u pattern, we usually don't have the ln in our expression yet. Usually we don't see the ln until after we've anti-derived. So there's no reason we can't have the ln as part of our u, right? So let's anti-derive this, and the antiderivative of u prime over u is going to be ln absolute value of u. And in this case, the u itself is another ln function. We've got an ln plugged inside another ln. Let's not forget the 1/3 out front. And since we've just anti-derived, let's remember the plus c, and we can put a box around it. And there you have it. Now this is one that I believe is fairly easy to check just by differentiating, so let's do so. We know that when we derive this down here, this 1/3 will just hang out in front. Okay, now that I've got it copied up here, the 1/3 will be out in front. And we know that when we have the ln of something, the ln of this u, where the derivative is going to be u prime over u. So let's put the u down below, and the derivative of that u is going to be the 1 over x. The derivative of c here is going to be 0. This x up top can be brought down below. And this 3 out in front can be brought up into the exponent according to our log properties, ln of x cubed. Interesting to note that there's really no reason why we couldn't also bring this x up into the exponent and have x to the x power, or we could bring both the 3 and the x up into the exponent position. There are several possibilities, but if we're trying to match the original problem, we'll bring the 3 up there. And we see that now we do have something that matches our original integrand. So we'll call this one checked. All right, let's go on to the last exercise. All right, this last one is tricky. It's inspired by several of the exercises in our textbook, and every year those exercises cause massive headaches for students. Of course, I challenge you to try this one on your own before you watch me do it, but I assume you're watching the video because you've already tried it and need a little help. So this doesn't seem to fit any of our other patterns that we look for anti-deriving, so we'll try U-substitution. And the rule of thumb says to make u equal the function that's under the radical, if there's a radical present. Well, okay, we could set u equal to x, in which case du would be equal to dx, but notice that that really doesn't help us out at all. All that's going to do is it's going to replace all the x's with u's, and it's going to replace the dx with du, and we really haven't made any progress. That's essentially the same integral that as we started with. So our textbook offers a hint, and let's try it out. The textbook offers the hint that we should let u equal the entire denominator. And if it's not immediately obvious why that's going to be helpful, I don't blame you, but let's just roll with it and see where it takes us. Now, the denominator is taken care of when it comes time to U-substitute. So let's take a look at this dx now. Of course, we'll derive our u with respect to x. And when we derive the right-hand side of that equation, we'll get 1/2 x to the negative 1/2 plus 0. We'll bring the dx over. And if in the numerator, let's say for just a moment, let's imagine that we had a 1/2 x to the negative 1/2 up there in the numerator of the original integrand. Notice that we'd be in great shape. We wouldn't bother bringing this over to the left-hand side of the equation, because instead we would just say that all of this is present here in the original integrand. And we can then replace all of this with just a du, according to this equation, right? So look out for that in some problems. That does pop up sometimes where you don't need to get rid of all this stuff on the right-hand side of the equation. However, it doesn't really help us out in this particular problem. We don't have a 1/2 x to the negative 1/2 in the numerator. We've got an x to the positive 1/2 in the numerator. Felt like we were close there for a second, didn't it? So anyway, in this case, let's go ahead and bring all of this over to the left-hand side of the equation. Let's go ahead and get this dx all by itself. And when we do that, we'll get a 2x to the positive 1/2 du on the left, and then we'll have the dx by itself on the right. Now this does present us with a bit of a problem, because remember the idea of U-substitution is that we're trying to replace all of these x's and dx's with u's and du's respectively. And now the thing that we're replacing dx with, it has a du, which is fine, but it's also got an x in there, and we didn't want that x in there. So what do? Do you see what we might be able to do to fix that? Well, we're going to refer back to this original u definition. Notice that we can rearrange that. We can rearrange that to get x to the 1/2 equals u minus 5, right? And then I can substitute that in to this equation over here, and that can give me an expression on the left-hand side completely in terms of u and du. So let's do that. Let's write this as 2, and instead of x to the 1/2, we'll put this u minus 5 du equals dx. So pause if you need to. Make sure you completely got that. And turns out we inadvertently did ourselves a favor as well, too. The last thing that we need to handle in the original integrand is this root x. And notice that we've just handled that. So we're ready to U-substitute now. So we are going to take the indefinite integral. That root x up there we'll replace with a u minus 5 here. The root x plus 5, that's going to be replaced with the u. And this dx is going to be replaced with the 2 quantity u minus 5 du. So there is our U-substituted integral. All right, let's bring this 2 to the outside. So 2 integral. Let's distribute out the u minus 5 times another u minus 5. That's going to give us u squared minus 10u plus 25 all over this u, and then du. Let's further simplify here. U squared divided by u is going to give us u. Minus 10u divided by u is going to be minus 10. And plus 25 over u will give us plus, and let's anticipate, let's look ahead. Let's say plus 25 times 1 over u. And I'm doing that because this fits our derivative of logarithm pattern. That's our u prime over u, so to speak. I know that gets a little confusing because by calling that u prime over u, you may be looking for where's the u prime? Well, we've done the u substitution, so I hope you're following along with that. And integral to du. So we keep going. Let's see, the antiderivative of u is going to be 1/2 u squared. Antiderivative of 10, or minus 10, is going to be minus 10u. Plus 25, the antiderivative of 1 over u is going to be ln, absolute value of u. That's all being multiplied by 2, and we've got a plus c at the end since we've just antiderived. So let's simplify that. There we go. And let's substitute back in our original definition, or let's substitute back in our original x's. And if I further simplify that algebraically, I'm going to FOIL this out, x to the 1/2 plus 5 times x to the 1/2 plus 5, and then distribute this. And we are getting close, ladies and gentlemen. I believe this will be our last step. We've got an x here, plus 10x to the 1/2 minus 20x to the 1/2. That results in minus 10x to the 1/2. Let's do this one next. Plus 50 ln absolute value x to the 1/2 plus 5. And then finally, plus 25 minus 100. That's going to be minus 75 plus c. And I'll remind you of something that I brought up in a previous video, or I'm sure I must have brought up in class, that back here where we have a constant negative 75 plus some letter c that represents any constant in the world, well, we can just represent the both of those collectively as a plus c. We can merge those together into a single plus c. So let's do that. Plus c. And we'll put a box around it and call it a day. Wow, that was wicked, and you may be happy to hear that this is one of those that I'm going to admit there's not really an easy way to check this. So certainly come to office hours, or let's discuss in class how we might go about trying to ensure that we did this correctly.